You step outside, and the whole dome above you has a color, as if the air itself has been dyed. But if you look straight at the sun, the light doesn't look blue at all. So where is that blue coming from? If it isn't coming from the sun as a blue lamp, it feels like a contradiction you can't quite point to because the blue is everywhere and nowhere at once. Try a small experiment with your attention. Look at a patch of sky away from the sun, then look closer to the sun, then far to the side again. The brightness changes, but the blueness stays strangely consistent across directions on a clear day. That's the first clue. Whatever is making the color isn't a single spot in the sky. It's happening all through the air between you and space, like a faint glow spread through a volume. We often talk as if white light is one thing, but in everyday life, it's a mixture of many colors traveling together. A simple hint is a rainbow after rain. The same sunlight can be separated into different colors when it passes through the right conditions. So when sunlight enters the atmosphere, it's not bringing just one color to be painted onto the sky. It's bringing a full blend, and the air gets to decide how that blend is redirected. Imagine shining a flashlight through clear water in a dark room. You might see a bright path, not because the water glows, but because tiny things in the water send light sideways into your eyes. Air does something similar, even when it looks perfectly clean. The atmosphere isn't empty. It's filled with molecules, mostly nitrogen and oxygen, too small to see individually. They can intercept passing light and send a small portion of it off in new directions. Here's the key. Those molecules don't redirect all colors equally. Shorter wavelength light, toward the blue end of the spectrum, is scattered much more strongly than longer wavelength light, toward the red end. A useful name for this is Rayleigh scattering, scattering by particles much smaller than the wavelength of light, like individual molecules. The result is not that the air makes blue light, but that it preferentially throws blue light around the sky. Now the earlier contradiction starts to loosen. When you look at the sun, you're mostly seeing direct light that has traveled in a straight line, still containing the full mix of colors. When you look away from the sun into the sky, you're mostly seeing light that has been redirected toward you by the air. That redirected light has been filtered by scattering. It's richer in blue because blue is the color the air tosses around most efficiently. This also explains why the sky can look deeper blue overhead than near the horizon. When you look toward the horizon, your gaze passes through a longer stretch of atmosphere. Along that longer path, more light is scattered and mixed, and additional effects, like dust, water droplets, and pollution, often become more important. Even in fairly clean air, the longer path tends to wash the color toward a paler blue, sometimes leaning whitish. A natural question follows. If shorter wavelengths scatter more, why isn't the sky violet instead of blue? Part of the answer is simply the sunlight itself. The sun provides less violet light than blue light. Another part is that some violet is absorbed in the upper atmosphere before it can contribute much to the sky's glow. And finally, our eyes are less sensitive to violet. So even when violet is present, it doesn't dominate our perception the way you might expect. Notice what this means. The blue sky is not a surface color, like paint on a wall. It's light arriving from countless directions after being redirected by countless molecules. In that sense, the sky is more like a gentle, uniform lampshade around the planet, lit by the sun and made visible by scattering. The color of the sky is really the color of sunlight after it has been reshaped by the atmosphere. Now, shift your attention to late afternoon. As the sun nears the horizon, its light must travel through much more atmosphere before it reaches you directly. Along that long path, the short wavelength blues are scattered out of the beam more and more, sent off into other directions. What remains in the direct sunlight is weighted toward longer wavelengths, warmer tones, so the sun and the light near it can look yellow, orange, or red. That's why sunsets can feel like two stories happening at once. The sky away from the sun may still hold on to blues higher up because scattered light is still filling the dome. But the light coming straight from the sun has been depleted of blues by the time it arrives at your eyes. The same process. Selective scattering creates both the blue day and the warm sunset, depending on how much air the light passes through. Clouds and haze give a useful contrast. Cloud droplets are much larger than air molecules, and they scatter many colors more evenly, which is why clouds often look white or gray rather than strongly blue. Haze and smoke can add particles of various sizes that change the balance, sometimes whitening the sky or making sunsets more dramatic. So the classic blue sky is most vivid when the air is clean and the scattering is dominated by molecules. If you take one idea with you, let it be this. The atmosphere is not just a passive window. It's an active participant that redirects light, and it does so unevenly across colors. The sky's blue is the signature of tiny scatterers, molecules spreading short wavelength light across the dome of your view. And once you see it that way, the color overhead becomes less like a backdrop and more like a constant, quiet interaction between sunlight and air.